I, with my colleagues, aim to discuss the area requirements for offshore wind parks, focusing on the effects of wakes and on overall resource availability. Our focus area is the southern North Sea, which is home to multiple operational and developing offshore wind projects. In this context, we recognize the importance of coexistence among various sectors, including fishery, military, energy, and the environment, while primarily addressing the technical aspects of the problem here. The determination of area requirements for offshore wind parks relies on accurate wind assessment, specifically wind modeling. This is crucial because the wind and wake characteristics differ significantly between large and small wind parks. Wind assessment involves creating wind resource maps, such as the one shown here, which displays the average offshore wind speed at 150 meters above the mean sea level and the average monthly capacity factor for the period between 1996 and 2019 based on NORAD 3-kilometer reanalysis data. Capacity factor is estimated for a 15 megawatt turbine. By utilizing this resource mapping and considering turbine characteristics such as power curves and capacity factor, we can analyze wind, wake, and power production variations for different turbine types. This information helps in identifying areas that are less susceptible to wake effects. The interference caused by wake effects or aerodynamic losses between turbines can be minimized by adopting a larger spacing between turbines, typically around 10 to 15 rotor diameters. However, for offshore wind turbines with a diameter of approximately 200 meters, this requires a spacing of a couple of kilometers, leading to increased transmission costs and a significant expansion of the project area, among others. Such considerations can potentially create conflicts with other sectors and stakeholders also. To manage the project within a smaller area, advanced control methods can be employed to steer and redirect the wake as demonstrated here. Furthermore, the presence of wakes can enhance intermittency in wind energy generation caused by nonlinear interactions between wind speed and power generation. Control methods can also help to reduce such intermittency caused by wakes. The first crucial step in determining the optimal location of wind turbines within a wind farm is to utilize a reliable and accurate wake model to both predict the turbine-induced wakes and resolve the complex interactions between turbines and wind farms within a cluster of offshore wind parks. This figure shows one of the attempts to simulate the annual mean wind speed depicts in the southern North Sea, that is fortunately our focus area. This area hosts a large cluster of wind parks. The figure shows that reduction in the annual mean wind speed reaches up to 2.5 meters per second during prevailing southwesterly wind. These deficits also show dependency on the wind park geometry, so that in this case wake can extend about 35 to 40 kilometers in downwind direction, as you can see here. While this effort provides very good insights on the effect of wind speed in a large cluster of wind parks, it is not able to resolve effects and interactions of turbines within a wind park. This is because we need to capture not only mesoscale variations and variabilities, but also microscale flow fields affected by turbines within the area of an operational or planned wind park. It is important to highlight that climate and weather models reveal chaotic behavior with high sensitivity to input uncertainties. In the context of wind energy, these models face additional challenges due to the uncertain parameterization of turbine and farm effects within mesoscale models, as well as the nonlinear interactions between farm parameterization and other model parameterizations that amplifies the overall uncertainty in the model. To address these challenges, we have developed two advanced multi-scale modeling frameworks capable of capturing a wide ranges of scale, from meso to micro scale. By micro scale, I mean turbine and blade related scales. Today, I will present the results obtained from one of these numerical systems known as SADLES. Further information is provided in another video addressing the results of the work package 2 of the EU project HIPERWIND. We have selected wind parks located in the vicinity of Alpha Ventus wind park in German Bight as our case study. This is Alpha Ventus and other neighboring farms. By analyzing the impact of the wind farm in the southwest in the absence of control system, we have observed a significant reduction in the ambient wind speed at Alpha Ventus by around 14% and the turbine power output by approximately 35%. Capacity factor may change more than 20%. These findings highlight the importance of considering the effects of wind farms on the local wind climate and their potential consequences for energy production. Because the flow through and around large wind farms are significantly different from the flow through and around smaller wind farms, the area requirements to design and plan an offshore wind park project depend then strongly on wind resource assessment and wake modeling. While mesoscale models in their finest grid are exposed to lots of uncertainty in resolving the relevant scales for this problem, multi-scale framework, by accounting better representation of wind turbines and small-scale variabilities, can provide very accurate information on wake generation, interaction, and evolution in the area within the large cluster of wind parks. These models provide lots of benchmark to cover wide range of atmospheric stability conditions and physical processes, specifically during transient events that can be used to develop and train existing engineering models for layout optimization and control, for instance.